Part 1. The basics. Matter can neither be created nor destroyed, it can only be changed. This is a paraphrase of the law of conservation of mass, which was first formulated by the French chemist Antoine Lavoisier in the late 18th century. Lavoisier is often regarded as the father of modern chemistry due to his work in establishing this fundamental principle. As we shall see when we look at the rock cycle, this applies to rocks as much as anything else. We shall discover that one kind of rock can change to any other kind of rock. It can even change back to itself. It just takes time, lots and lots and lots of time. So what is a rock? A rock is a naturally occurring solid aggregate of minerals which forms part of the Earth's crust. Rocks are classified into three main types, based on their formation processes and mineral composition. Igneous, formed from the solidification and cooling of molten magma or lava. Examples include granite and basalt. Sedimentary, originate from the accumulation and compression of sediments which can be fragments of other rocks, organic matter, or minerals. Examples include sandstone and limestone. Metamorphic, formed when existing rocks are transformed by heat, pressure or chemically active fluids, without melting. Examples include marble and slate. Each type of rock has unique characteristics depending on its mineral content and formation history. What is a mineral? Minerals are the main constituent of rocks. They are homogeneous, naturally occurring, inorganic solids. Each mineral has a definite chemical composition, for example quartz, SiO2, calcite, CaCO3, hematite, iron oxide, Fe2O3, or fluorite, calcium fluoride, CaF2. And each has a characteristic crystalline structure such as cubic or rhombic. Alternatively, a mineral may be a single element such as copper, Cu, or gold, Au. About 2,500 different minerals have been described. Here are some other common rock-forming minerals. Feldspar, garnet, augite, olivine, mica, hornblende. There are three main types of rock: igneous, formed by the cooling of molten material from the Earth's mantle, known as magma. Sedimentary, the result of the deposition, compaction and cementation of eroded rocks, called sediments. Metamorphic, rocks whose structure or composition has been changed by heat, pressure or both. Rock texture describes the shape and the relationship between the mineral grains. In igneous rocks, the mineral grains have an irregular shape and are interlocking. The orientation of the grains is random. Sedimentary rocks normally comprise discrete grains which are often rounded. There may be some alignment of the grains. Metamorphic rocks have irregular shaped grains, and platy minerals are aligned or distorted. Part 2. What type of rock is this? Let's imagine we're out for a walk in the countryside. Something catches your eye, maybe a strange shape or a sparkle of light. You bend down and pick up a stone and ask yourself, what kind of rock is this? What clues can we find to help us? What tools can I use to help identify this rock? Looking at rocks in the field. Features you might be able to see with the naked eye. What color is it? Be careful though. Color is not always a reliable indicator due to weathering. For example, look at the recently collapsed stones in this old Cotswold stone wall. How heavy is it? Does it seem unduly heavy or light for its size? What shape is it? Is it round, angular, irregular, or flat? Is it hard and solid, or is it easily broken or crumbly? How does it break? With an irregular edge, or is it blocky, or rounded, conchoidal? Does it break in a fissile way, into thin sheets, or along bedding planes? Does the rock have any apparent structure? Can you see any layers, folds, fractures or veins? Can you see any fossils in the rock? I wish you'd brought your hand lens with you. You've got it? Brilliant. Let's use it to find out more detail. Texture. Does the rock seem smooth, rough, or crystalline? If you can see any mineral grains, what are they shaped like? Do they appear angular, rounded, regular, interlocking, or aligned? What about the size of the grains? Are they large, say, over 2 millimeters, medium, fine, invisible, or glassy? Do the grains appear to be well sorted, variable or unsorted, or even sorted into distinct layers? Do the grains appear to have grown into each other, or are they relatively distinct from each other? What's holding the rock grains together? Can you see any kind of cement? Are the grains aligned together or do they seem random? Analysis in the laboratory. Using a polarizing microscope, what type of minerals can I recognize? Matrix or cement? What's holding the rock grains or minerals together? Are there any microfossils, for example, foraminifera, which are not visible to the naked eye? Does the rock fluoresce under UV light? If so, then it may contain hydrocarbons. Chemical analysis. Acid test. Does the rock fizz in weak acid? If so, it contains calcium carbonate material. Is it radioactive? Be careful. Isotopic analysis. This may make it possible to date the rock using the relative ratio of different isotopes, for example, potassium K40 to argon Ar40. The potassium isotope takes 1.25 billion years for half its amount in a sample to decay to argon Ar40. Mass spectroscopy can determine the detailed chemical composition of the rock. Part 3. The rock cycle.
No vestige of a beginning, no prospect of an end.
James Hutton, Scottish geologist, 1726 to 1797, the father of modern geology. The following short video will show you all the things that can happen to a rock after its formation. I think you may find it quite surprising, and certainly supports James Hutton's famous quote. Understanding the rock cycle. Let's take a quick look at the rock cycle. Here's a diagram showing the rock cycle in the Earth's crust. What it shows are the different types of rocks and how they can change over time. Let's go through a quick example. Here is a chunk of an igneous rock known as granite. You can see it's made up of integral crystals of potassium feldspar and quartz and biotite, and that's what gives it its speckled look. Now, as we mentioned, granite's an igneous rock, which forms from the solidification of melted material, magma or lava. Granite happens to form deep underground from the slow cooling of magma. But the question we want to look at now is what can happen to this igneous rock over time, and there's a handful of possibilities. The first thing that could happen is our granite could be lifted up, forced up from beneath the ground where it's exposed to weathering and erosion by the wind, the rain and ice. These forces break this rock down into little pieces called sediments. So now our granite has been broken into small pieces of granite. Now these sediments can be deposited and buried and then compacted and cemented together to form a brand new rock called a sedimentary rock, like this piece of sandstone. So simply by weathering and eroding the granite into sediments and then squeezing the sediments back together, you've converted your igneous rock into a sedimentary rock. But that's not the only thing that can happen to our igneous rock. What if it is pushed even deeper underground by the movement of Earth's tectonic plates, so it is exposed to intense heat and/or pressure, causing it to metamorphose or recrystallize into a metamorphic rock, like this piece of gneiss seen here? So with the simple addition of some heat and pressure, we've turned our igneous rock into a metamorphic rock. But there's still one more option. What if our igneous rock is exposed to intense heat, causing it to melt and return into liquid state of magma? Well, it can then of course cool and solidify again, giving us another igneous rock. But maybe this time it will cool quickly and give us something with smaller crystals, or maybe no crystals at all, like this piece of obsidian. So what you can see is that on the rock cycle, any rock is able to turn into any other rock when exposed to the different processes in and on the Earth's surface. Remember, we start with these three types of rocks. These are our three classifications, and from them we can go to anything else. Again, let's look at the igneous rock. We know that igneous rock is formed from melting into magma and solidification, but remember it can melt again, and that process can happen over and over and over again. So I can have an igneous rock that becomes igneous again, maybe a different kind of igneous rock, but any rock can melt into magma and form an igneous rock as seen in the previous diagrams. Sedimentary and metamorphic rocks, they can all be melted and ultimately result in an igneous rock forming. Let's look at the sedimentary rocks now. Remember, these form from sediments which have been deposited and buried under pressure, causing them to compact and cement together. But of course, any rock can be weathered into sediments, and therefore any metamorphic or igneous rock can become a sedimentary rock. Finally, we have our metamorphic rock, and remember, these formed when rocks are exposed to intense heat, pressure, or both. But of course, that process can take place with any type of rock, sedimentary, igneous, or even metamorphic rocks. So the key idea behind the rock cycle is the fact that any rock can become any other kind of rock. It can even become itself. Change is always taking place. It's generally slow over many millions of years. However, the results can be impressive. Now we'll look at the formation, composition, and characteristics of each of the three rock types.
In the depths of the earth, igneous rocks form in a crucible of heat, a foundation for continents and mountains alike.
Before discussing igneous rocks, it's worth taking a look at that mysterious place where they are formed, the Earth's mantle. After all, if the rock cycle can be said to have a starting point anywhere, it's in the molten part of the upper mantle. First off, where is it? The mantle lies between the Earth's outer core and the crust. It is by far the thickest layer of the planet, accounting for some 84% of its volume. The upper mantle is the region that extends from just beneath the crust to a depth of about 670 kilometers. It includes both the rigid lithosphere and the more ductile asthenosphere. The lower mantle extends from 670 to 2,900 kilometers, where extreme pressure and heat, ranging from 1,000 to 3,700 degrees Celsius, cause the rock to behave in a more fluid manner despite being solid. This creates convection currents in the mantle, and the heat and pressure of these makes the asthenosphere flow, driving the tectonic plates, forcing molten material upwards to be extruded through rifts in the lithosphere at constructive plate margins as new oceanic crust in the form of slowly flowing lava via effusive volcanoes, which subsequently encounters less dense continental crust and is subducted beneath it at destructive plate margins, or subduction zones. Partial melting of both the oceanic and some of the continental crust forms magma, which is intruded into the continental crust as subsurface batholiths and plutons, and partly as lava via explosive volcanoes. This also causes organic material from the ocean floor to get mixed in, which brings a source of carbon to the magma. The overall classification of igneous rocks is by their environment of formation. 1. Extrusive. Ejection of molten material directly onto the Earth's surface in the form of lava. This is characterized by rapid cooling and a consequent small crystal size. 2. Intrusive. In this case, molten material is forced into crustal rocks as magma and cools slowly at depth, giving rise to larger crystals. There are essentially two types of extrusive volcanoes, effusive and explosive, and they differ according to, amongst other things, the energy of the eruption, the composition of the lava, and the circumstances under which the eruptions occur. Effusive volcanoes. These are commonly known as shield volcanoes due to their relatively gentle, non-explosive eruptions, which emit a type of low-viscosity lava that flows smoothly and steadily over a large area, forming a low-domed structure rather than a cone. The lava is rich in mafic minerals, magnesium and iron, and relatively low in silica. The cooling rate is relatively rapid, so rocks have fine-grained texture. They usually occur at constructive plate margins, for example the Mid-Atlantic Ridge, Mauna Loa in Hawaii, and the most recent Sund-Núna-Giga crater row in Iceland. The most common rock thus formed is basalt. Explosive volcanoes. These are generally known as composite or stratovolcanoes as they are built up of layers of solid lava from successive eruptions, giving them the form of a steep cone, as the lava is more viscous than that in shield volcanoes and so does not spread as far. The higher viscosity is due to a greater volume of intermediate to felsic minerals, silicon and aluminium, which makes the originating magma less fluid and more prone to trapping gases, especially water vapor, carbon dioxide and sulfur dioxide, leading to explosive eruptions. In addition, composite volcanoes emit pyroclastic flows of hot, fast-moving clouds of gas, ash, and volcanic debris that can flow down the slopes of the volcano at very high speeds, up to 700 kilometers per hour. As with effusive volcanoes, the lava cools quickly and so produces rocks with small crystal sizes. They are typically found at convergent plate boundaries, where oceanic crust subducts beneath continental crust and melts, causing lava and gases to rise under high pressure and explode as volcanoes. Composite volcanoes produce a range of igneous rocks, with andesite being the most common. However, depending on the magma's composition and eruption style, they can also form dacite, rhyolite, and early in the eruption, basalt. Trapped gases also form vesicular varieties of these. The violence of the eruptions also gives rise to the formation of pyroclastic rocks such as tuff, pumice, and ignimbrite. Examples of active explosive composite volcanoes are Mount St. Helens in the US, Mount Fuji in Japan, and in Italy, Mount Vesuvius, Mount Etna. Conversely, magma may rise through the Earth's crust along fissures and weaknesses and cool slowly beneath the surface in what is known as an intrusive environment. It rises from the mantle because it is less dense than the surrounding rock, but may cool and solidify before reaching the surface, with the slow cooling giving rise to rocks with large crystals. This movement may occur for several reasons. Tectonic plate movements. Plate convergence. At subduction zones, one tectonic plate sinks beneath another, causing melting in the mantle. The magma generated can rise into the crust, forming intrusive bodies. Continent-to-continent collision. Intense pressure causes melting and subsequent intrusion. Plate divergence. At mid-ocean ridges and continental rifts, plates pull apart, allowing magma from the mantle to rise and fill the gap, sometimes forming intrusive structures. Hotspots, mantle plumes, or upwellings of abnormally hot rock, can cause localized melting and magma generation, leading to intrusive activity beneath both oceanic and continental plates. Crustal weaknesses. Fractures and faults in the Earth's crust provide pathways for magma to rise. Magmatic intrusions can form a variety of structures. This diagram, which looks to me like it was painted by Salvador Dali, shows a number of these with the surrounding country rocks stripped away so that you can get a better look at them. Batholiths. Batholiths, not shown on this diagram, are massive, irregularly shaped bodies of intrusive igneous rock, often covering hundreds to thousands of square kilometers. They typically have a granitic composition, and are the source of many of the structures shown in the diagram. They often form the core of mountain ranges. Examples: the Sierra Nevada batholith in California and the Cornubian batholith in southwest England, which is exposed to form Bodmin Moor and Dartmoor. Pluton. Pluton is a term used broadly for any crystallized magma body formed underground, as is the adjective plutonic. Example: the Pikes Peak Pluton in Colorado. Xenoliths. Although not intrusive structures, xenoliths, from the Greek for foreign rock, are chunks of the original country rock which have fallen into the magma and survived melting. Boss. A boss is a small, dome-shaped plutonic intrusion, usually less than 10 square kilometers in size. Laccoliths. Laccoliths are dome-shaped, mushroom-like intrusions that push up the overlying rock layers into a convex shape as magma accumulates beneath them. Magma intrudes between layers of sedimentary rock near the surface, creating a bulge in the overlying strata without breaking through to the surface itself. Example: the Henry Mountains in Utah. Dikes. Dikes are vertical or steeply inclined, sheet-like intrusions that cut across existing rock layers or fractures. Magma forces its way through cracks in the rock, often perpendicular to existing layers, forming a narrow, vertical intrusion that solidifies. Example: the Great Dike of Zimbabwe, a major geological structure containing valuable mineral deposits. Numerous dikes may be intruded simultaneously in close proximity to each other. This forms what is known as a dike swarm, like this example in Aigua Blava, in Spain. Ring dikes. Ring dikes are circular or elliptical steeply inclined intrusions that form around a central collapse zone or volcanic caldera. Ring dikes form when a magma chamber collapses, causing magma to be injected into a circular fracture around the central collapse, forming a ring-shaped intrusion. Example: the Glencoe Ring Dike in Scotland. Cone sheets. Cone sheets are circular cone-shaped intrusions that radiate outward and dip downward from a central point, often associated with volcanic centers. They form when magma is injected into concentric, downward-sloping fractures around a volcanic intrusion, spreading outward like a cone. Example: the Isle of Mull in Scotland, which has a famous cone sheet complex. Pipes. Pipes are cylindrical vertical conduits through which magma or volcanic gases travel toward the surface. These structures can form solid columns of intrusive igneous rock if the magma cools before reaching the surface. If solidified underground, pipes form a vertical igneous body. Example: kimberlite pipes, often associated with diamond deposits, such as the Kimberley mine in South Africa. Sills. Sills are horizontal or near-horizontal sheet-like intrusions that form parallel to the existing bedding planes. Magma intrudes between layers of existing sedimentary or metamorphic rock, solidifying into a flat, sheet-like structure. Example: the Wyn Sill, which stretches across northeast England, including parts of Northumberland, County Durham, and Cumbria. These intrusive features reflect the various ways magma interacts with and alters the Earth's crust, producing a wide range of geological structures, many of which are critical for understanding mountain formation, mineral deposits, and volcanic processes. Here are some examples of igneous rocks based on their environment of formation, crystal size, and texture. If the rate of cooling is almost instantaneous, then there is no time for crystals to form and you get a glassy obsidian, or possibly a basaltic glass. The most common fine-grained extrusive rock is basalt. Other fine-grained, extrusive rocks are andesite and rhyolite. If any of these contain gas pockets, they are called vesicular andesite, vesicular rhyolite, or vesicular basalt respectively. Examples of other vesicular rocks are pumice and scoria. One igneous rock that forms close to the surface and has a medium grain size is diabase. Having just looked at the extrusive igneous rocks, which form from molten material ejected from effusive or explosive volcanoes as lava, let's take a look at the other type of igneous rocks which form from magma intruded into the surrounding crustal rocks. In the case of these, the magma doesn't reach the surface and thus takes far longer to cool, thus giving rise to a much coarser texture and larger grain size than in the extrusive rocks we've already seen. The environment of formation for such rocks is known as intrusive or plutonic, and as with extrusive rocks, they are classified by their grain size and texture. Here are a few examples. Coarse-grained rocks with crystal sizes between 1 and 10 mm, granite, diorite, gabbro, peridotite, and dunite. Pegmatite is a very coarsely textured rock with crystal size over 10 mm. The other main criterion for classifying igneous rocks is the mineral composition of the original magma or lava. This involves measuring the relative percentages of minerals in the sample. In addition, the rock's color, density and chemical composition are taken into account, although you need to be careful with color, as minerals can form in variety of colors. There are 4 main subdivisions based on mineral composition. Acidic, or felsic, contain lots of feldspar and quartz. Intermediate, contain virtually no quartz, but more plagioclase, biotite mica and amphibole. Basic, or mafic, contain mainly pyroxene, olivine and plagioclase, which are rich in magnesium and iron. Ultrabasic, contain mainly olivine, and some pyroxene, and are thought to be similar in composition to the Earth's mantle. Sedimentary rocks.
Rocks, remember. Every grain, every layer, tells a story of what once was.
Sedimentary rocks fall within 3 groups, depending on the composition of the sediment. Clastic or fragmentary sediments are formed from fragments of pre-existing rocks or minerals, transported by physical processes like water, wind, or ice, and deposited in various environments. Biological sediments, also known as biogenic sediments, are formed primarily from the remains of living organisms. These sediments are rich in organic materials or skeletal remains of marine or terrestrial organisms. Chemical sediments form through the precipitation of minerals from water due to chemical reactions. This occurs when dissolved minerals in water reach supersaturation, or when evaporation or chemical changes cause the minerals to precipitate out of solution. This highly generalized diagram shows the various environments of deposition of clastic, biogenic and chemically derived sedimentary rocks, together with some of the rock types commonly associated with them. It's quite detailed, so you may want to pause the video at this point to study it. Clastic sedimentary rocks are classified by their grain size, the shape of the grains, and their chemical composition. These will also help to identify their origin, the type of erosion and transport they have undergone, and well as the environment in which they were deposited. A rock which has large rounded gravel-sized grains, greater than 2 mm, is likely to be a conglomerate. However, if the grains are angular, it will be a breccia. One which has either rounded or angular grains, which are between 0.0625 and 2 mm, will usually be a sandstone. Siltstone has very fine grains, ranging between 0.0039 to 0.0625 mm. Clay-sized grains of less than 0.0039 mm, with fine layers that may split easily, indicate shale. However, the absence of layering, and indistinguishable grains, means the rock is likely to be claystone. Halite is a chemical sedimentary rock, primarily composed of sodium chloride, NaCl, commonly known as table salt. It forms through the evaporation of water in saline lakes, seas, or inland bodies of water, where salt becomes concentrated and crystallizes out of the solution. Gypsum is a soft sedimentary rock composed of calcium sulfate dihydrate, CaSO4.2H2O. It forms through the evaporation of water in areas such as shallow marine environments, lakes, and inland seas, similar to halite but at slightly lower salinities. Limestone is a common chemical and biogenic sedimentary rock primarily composed of calcium carbonate, CaCO3, often in the form of the mineral calcite. It forms in marine environments where shells, coral, and skeletal fragments of marine organisms accumulate, as well as through the direct precipitation of calcium carbonate from water. Dolomite is a chemical rock primarily composed of the mineral dolomite, CaMgCO3. It forms through a process called dolomitization, where magnesium-rich waters alter limestone, composed of calcium carbonate, by replacing some of the calcium with magnesium. This often occurs in shallow marine environments. Coal is an organic sedimentary rock formed from the accumulation and compaction of plant material, typically in swampy or low-oxygen environments where organic matter doesn't fully decay. Over time, heat and pressure transform the plant debris into coal through a process called coalification. Metamorphic rocks.
Nothing is lost, nothing is created. Everything is transformed.
As we have seen in the rock cycle, existing rocks can be affected by heat, pressure, or both to the point where their structure and composition are changed to a greater or lesser degree. One point to note though, is that the rocks are never melted as part of the metamorphic process. True, they may be heated to a very high level, but if they were to actually melt, they would simply revert to a fluid state, and probably become igneous rocks again one day. Metamorphic rocks may display banding, although this usually bears no relationship to the original bedding, and in certain metamorphic regimes will become foliated. Also, the degree of energy required for the reformation of the subject rock indicates the grade of metamorphism undergone. This ranges from low grade to high grade. The energy involved may vary from relatively gentle burial, with low pressure and heat, low-grade metamorphism, as is found with the metamorphosis of shales or clays into slates and phyllites, Or it may range up to intense pressure where the original rock is so completely pulverized that it is totally recrystallized, high-grade metamorphism, as is the case with myelinite, which may originate from almost any other form of rock. Between these are the four basic forms of metamorphism: burial, regional, contact, dynamic. This diagram may help to explain why and where they occur, and the effects each has on the surrounding rock. Burial metamorphism. Burial and compression beneath high loads of later sediment. This typically occurs in deep sedimentary basins, such as those found along continental margins or in areas of thick sediment deposition. At relatively low temperatures and pressures, shales are transformed into slate or phyllite, possibly with foliated textures. Dynamic metamorphism. Along fault zones, pressure is the dominant force and the rock is subjected to intense shearing and mechanical stress rather than heat. It happens at all levels in the Earth's crust, primarily due to tectonic movement. Intense shear stress destroys almost all of any original rock and causes it to reconstitute with very fine crystals. Example rocks are myelinite and cataclasite. Contact metamorphism. Around igneous intrusions, where magma heats the surrounding rocks, the high localized temperature affects the rock close to the intrusion, creating a metamorphic aureole, a zone of altered rock. It typically happens at shallow depths in the Earth's crust, where pressure is relatively low but temperatures are high due to the proximity of the magma. Here rocks are baked under very high temperature, which is capable of transforming shales into hornfools, limestone to marble and sandstone to quartzite. Regional metamorphism. Regional metamorphism occurs in large areas, typically at convergent plate boundaries during mountain building events. It happens when rocks are subjected to high pressure and temperature simultaneously over a broad area, usually during continental collisions or subduction. Key locations include mountain belts, for example, the Himalayas and Alps, and deep crustal zones where rocks are deeply buried. In these cases, rocks are deformed and may also recrystallize, often forming foliated textures. These processes would typically reform shale into schist or granite into gneiss. There are other examples of metamorphism, for instance shock metamorphism caused by the extreme forces of a meteorite impact, or hydrothermal metamorphism in which water with dissolved ions can change a rock's internal chemistry, for example serpentine from peridotite. Here are a few examples of metamorphic rocks and how they are classified. Slate is a fine-grained, grayish rock, which derives from the low-grade burial metamorphism of clay or other mudstones. Its principal minerals are quartz and muscovite mica, with secondaries of biotite, chlorite, hematite and pyrite. It has microscopically thin cleavage planes which bear no relationship to the original bedding. Instead, they are caused by the reorientation of its platy minerals perpendicular to the direction of compaction. Slate splits easily into smooth, flat sheets, and it is often used in roofing, flooring, and writing surfaces, as well as the bed for all professional snooker and pool tables. Phyllite is formed from slate that is further metamorphosed so that very fine-grained muscovite mica achieves a preferred orientation. It is primarily composed of quartz, sericite mica, and chlorite. Phyllite has larger grained mica grains than slate and, among foliated metamorphic rocks, it represents a gradation in the degree of metamorphism between slate and schist. Its minute crystals of graphite, sericite, chlorite, or the translucent fine-grained muscovite mica impart a silky, sometimes golden, sheen to the surfaces of cleavage, called phylitic luster. The foliation is commonly crinkled or wavy in appearance. Phyllites are mostly used in decorative aggregates, interior decors, building stones, facing stones, garden decoration and curbing. Cemetery markers, commemorative tablets and creating artworks are some of its commercial uses. Schist is an intermediate to high-grade metamorphic rock that forms under moderate to high temperatures, around 300 to 600 degrees Celsius, and pressures, typically deep within the Earth's crust. Its formation conditions surpass those of low-grade rocks like slate, but are less extreme than those for high-grade rocks like gneiss. Schist is rich in platy minerals such as biotite and muscovite mica, along with others such as garnet, quartz, staurolite, and kyanite, which are stable at these higher-grade regional metamorphic conditions. These minerals align under pressure, creating the rock's distinct foliated texture, often with a shiny, layered appearance. Gneiss is a type of metamorphic rock characterized by its distinct banded or foliated appearance, which results from the high-grade metamorphism of original igneous or sedimentary rocks. It forms under extreme heat and pressure conditions, usually deep within the Earth's crust, which reorganizes minerals into visible layers or bands. Key features of gneiss include the light and dark mineral bands, often alternate in parallel layers. Light bands are typically rich in minerals like quartz and feldspar, while dark bands contain more biotite, hornblende, or other mafic minerals. It is coarse-grained, and individual mineral grains in gneiss are usually large enough to see with the naked eye. Gneiss can form from various protoliths, including granite, sandstone, or shale, depending on the conditions of metamorphism. Based on composition and origin, gneiss can be further classified as orthogneiss, from igneous rock, usually granite, or paragneiss, from sedimentary rock. Gneiss is commonly used as a building and decorative stone due to its durability and visually striking appearance. We'll now take a look at some examples of non-foliated metamorphic rocks. Anthracite coal is a low-grade metamorphic rock that represents the final stage of coalification. It forms from bituminous coal under conditions of intense heat and pressure, usually in tectonically active regions where pressures and temperatures are high, such as in fold belts or areas of mountain formation. It comprises 86 to 98% pure carbon, giving anthracite its high energy content and clean burn properties. Minor amounts of sulfur, nitrogen, and other minerals may be present as trace elements. Anthracite is considered a regional metamorphic rock, formed over large areas due to high pressure and moderate to high temperatures. Anthracite has the highest energy content of all coal types, making it highly efficient as a fuel. Hornfels is a fine-grained metamorphic rock that forms through contact metamorphism, where pre-existing rocks are altered by intense heat from nearby magma intrusions. This heat causes recrystallization of minerals without significant pressure, leading to a hard, dense, and often splintery texture. Hornfels is known for its toughness and can produce a ringing sound when struck due to its hardness. The composition of hornfels varies based on the protolith, typically either a sedimentary rock such as shale or limestone or an igneous rock such as basalt. It commonly comprises quartz, feldspar, mica, and sometimes pyroxene. Accessory minerals, for example garnet, cordierite, or andalusite, may form under certain temperature conditions, especially in alumina-rich protoliths like shale. Hornfels has a dense, fine-grained texture with roughly equigranular crystals. It is often banded, especially when it forms from the metamorphism of sedimentary rocks. It represents a low to intermediate metamorphic grade, since it forms primarily through heat with minimal pressure. The grade can vary somewhat depending on proximity to the heat source, but it does not reach the high-grade conditions of regionally metamorphosed rocks. Hornfels is commonly used in construction as aggregate material, and due to its hardness, it is occasionally used in specific architectural applications where a durable stone is needed. Quartzite is a hard, non-foliated metamorphic rock that is primarily composed of quartz grains. It forms from the contact metamorphism of sandstone through intense heat and low pressure. This process causes recrystallization, leading to the interlocking of quartz grains and the elimination of any porosity found in the original sandstone. Whilst quartzite is mainly composed of quartz, typically over 90%, it may also retain minor amounts of other minerals such as feldspar, mica, and various impurities that may be present in the original sandstone. It has a granular texture, and the individual quartz grains are often visible. The rock is typically dense and very hard, making it resistant to weathering and erosion. Quartzite can vary in color, ranging from white to gray, red, pink, or even green, depending on the impurities present during its formation. Iron oxide can give it reddish hues, while other minerals can impart various colors. Quartzite typically forms at a medium to high metamorphic grade, often associated with regional metamorphism where significant tectonic forces are at play. Its hardness and durability make it suitable for various applications, including construction and landscaping. Marble is formed from the recrystallization of limestone or dolostone during contact metamorphism under high temperature and pressure. It is primarily composed of calcite, calcium carbonate, or dolomite, calcium magnesium carbonate, and is known for its ability to take a high polish and its extensive use in sculpture and architecture. The dominant mineral in most marbles is calcite, contributing to its white, grey, or colored appearance. However, in dolomitic marbles, magnesium replaces some of the calcium in the calcite structure. It may also contain small amounts of quartz, mica, pyrite, or graphite, which can influence color and texture. Marble typically exhibits a fine to medium-grained texture, with interlocking calcite or dolomite crystals. It can range from very homogeneous, uniform color, to highly varied with prominent veining and patterns, depending on the impurities present in the original limestone. While many marbles are white or gray, they can come in a variety of colors: green, pink, yellow, black, due to mineral impurities, such as iron oxide, clay, or organic materials. Marble generally forms at a low to medium metamorphic grade, indicating it typically experiences lower temperatures and pressures compared to rocks like schist or gneiss. Marble is highly valued for its aesthetic qualities and is used in various applications, including sculpture and art, architecture and interior decor. Metaconglomerate is a type of metamorphic rock that forms from the metamorphism of conglomerate, which is a sedimentary rock composed of rounded clasts, fragments, embedded in a finer-grained matrix. The metamorphic process involves exposure to heat and pressure due to contact with a magma intrusion, typically during regional metamorphism, which can occur in tectonically active areas such as mountain ranges, leading to changes in the rock's texture and mineral composition. The original rounded clasts in the conglomerate, which can be composed of various materials such as quartz, granite, or other rock fragments, are preserved in the metaconglomerate. The finer-grained matrix, the material surrounding the clasts, typically consists of quartz, feldspar and other minerals, and may become more crystalline during metamorphism. Metaconglomerate retains the original clast structure of the conglomerate, but the clasts may become flattened or elongated due to pressure, giving the rock a more foliate or schistose appearance. The matrix can become more recrystallized, making the rock denser and harder. Unlike many other metamorphic rocks, metaconglomerate may not exhibit pronounced foliation due to its composition and the preservation of clasts. However, if the metamorphic conditions are intense, some degree of foliation may develop. Metaconglomerate generally forms at a low to medium metamorphic grade, reflecting the conditions under which the original conglomerate was transformed. The specific grade can vary based on factors like temperature, pressure, and the duration of metamorphic conditions. Metaconglomerate is less commonly used than other metamorphic rocks, but may have some applications, including construction and decorative stone. Finally, here's a summary of all the rock types we've covered. Martin and Phil, thank you for watching this video, and we hope you've gained something from it. Why not also take a look at the others on our YouTube channel? In the meantime, goodbye and happy rock hunting.